This is joint work with Theo Untrau, and as the title says, so it's about equidistribution and especially quantitative aspects. So let me first recall the definition of equidistribution in the setting I'm going to work on. So very abstractly, equidistribution is some version of convergence of measures of probability measures on space. And the version I'm going to look at will be when you have a locally compact topological space, very often compact, but it could be something like the quotient of the upper half plane by a discrete group, which might have a finite volume and not be compact. We have some probability measure mu on X, which is kind of a reference measure to which other measures would like to converge. So mu n will be a sequence of measures, of probability measures again. Everything being happening on X. And the example to keep in mind for most of what I'm going to talk about, the standard example is when you have a finite subset non-empty in capital X, and then you look at the measure, which is just the average of delta masses over this finite subset. That's the standard example. And then we say that mu n becomes or is mu equidistributed as n goes to infinity. By definition means that you can compute the integral of suitable functions with respect to mu on the set capital X as limits of the corresponding integrals with respect to the measures mu n. Okay, so and in the example, this means the limit of the average of the test function f at the points in the finite subset that are varying. And of course, this statement for an arbitrary function f is way too strong to ask in general. And so one imposes restrictions on the test functions. And the classical definition for equidistribution is to assume that this works for f continuous and bounded. So if x is compact, this is just f continuous. If f is not necessarily compact, then we also assume that it's bounded. Okay, so this is a classical definition. Let me give one or two examples for those who might not be very familiar with it. One of the most basic ones goes back to Hermann-Weil in the early 20th century, is taking the space X to be the circle, or R mod Z, the measure mu to be the Lebesgue measure. And for instance, the Xn, so Hermann-Weil proved many statements of equidistribution of this kind, but the most basic one would be when you take the measures mu n to be defined as before by averaging over a finite set, and the set Xn would be the set of multiples up to n alpha for some element alpha, which is in R minus Q. Okay, and of course, alpha, 2 alpha, and so on have to be taken modulo Z. And then it's a fact that mu n or Xn, one could say, is indeed equidistributed according to Lebesgue measure when n goes to infinity. And it's a prototype of many statements of equidistribution. But just to give, so this is about, I think, 1917. And just to give another, in fact, even earlier example, even if it was not interpreted in this way at the time. So if you think of Dirichlet's theorem on primes in arithmetic progressions, it can be interpreted as equidistribution. In this case, the set X is just finite. It's the invertible classes modulo some fixed modulus Q. the set xn again. So the measure mu is the uniform probability measure on this finite set. And xn could be the set of primes. So you look at the set of residue classes p modulo q, let's say for primes p up to n. And you need p to be coprime with q if you want literally for this to be inside capital X. Okay, and then Dirichlet's theorem says that then there is equidistribution. Meaning that every congruence class modulo Q can be represented equally often, roughly speaking, by primes reduced modulo Q. Okay, and this example is a good example to see that it's very important very quickly to not only be able to say that equidistribution holds in the sense that these various limits that I've stated here exist and are equal to what they should be, but you also want to have more quantitative information. And that's for anybody who has studied any multiplicative number theory, one knows very well that Dirichlet's theorem on primes in arithmetic progression is just the beginning, and one really needs to have error terms and quantitative information. Need to have quantitative statements in many applications. So I'll give concrete example of such applications in quantitative terms, but for the moment, what do we mean by quantitative? So I'm going to stick to settings which are closer to the results like Hermann-Weil's than to Dirichlet's theorem. And so one of the easiest way is to say, well, we restrict the set of test functions, and we try to say that the left-hand side of the equality, the integral with respect to the limit measure, is equal to the nth term on the right-hand side, plus some explicit error term. And if you do this, there are many cases where you can do that, but it is not necessarily what's needed in applications. And for instance, maybe what most people most classically associate to the notion of quantitative equidistribution is the Erdős-Turan inequality. So this is maybe the first example, which has been studied for a long time. So the first version of this by Erdős and Turan is from 1948 to give an idea of the time scale. So this concerns the case, which is the one considered by Hermann-Weil. So the space is the circle, the limit measure is the Lebesgue measure, but it can apply in principle to any sequence of measures which can approximate mu. And it quantifies equidistribution by comparing the measure of intervals for the Lebesgue measure, so the length of an interval, with the corresponding measure for mu n. So in the case of the example, so this would be counting how many elements in your set belong to the interval. So how many elements in Xn belong to a given interval. So equidistribution in the case of the Lebesgue measure means that this goes to 0 when n goes to infinity. And the way it's quantified by Erdős and Turan is to take the supremum over all the intervals. And the interval, you can think of closed intervals or open intervals, it doesn't matter. And they find a quantitative upper bound for this, which depends on what are called the Weil sums for equidistribution. So the upper bound is of the following form. So it's bounded up to a multiple constant, which can be made explicit by 1 over t. So t is going to be some parameter which can be a real number that can be chosen arbitrarily, that usually is chosen to give the optimal possible bound. Okay, so maybe I should make clear that when I write this less symbol, it's the Vinogradov symbol, so it means that it's bounded by a certain constant times whatever follows. So in this case, so 1 over t, and then a sum over integers h in z with absolute value non-zero. So h is non-zero, but bounded by this capital T. And then I have something which decays with h, 1 over the modulus of h, times the modulus, or the absolute value of these Weil sums, which I'll call WH of mu n in general, which are in terms of integral, this would be the integral of the function exponential 2i pi n x to pi hx with respect to mu n. And again, in the case of the example, that is just averaging the additive character exponential 2i pi hx over the finite set xn. Okay. So if one looks at this inequality, then it reveals quickly that to have equidistribution is equivalent to having this WH of mu n go to 0. This is an old fact that was established by Hermann Weil in the same paper that I mentioned earlier. And this shows that if you know good bounds for these so-called Weil sums, then you will be able to provide an estimate for the supremum of this difference between the Lebesgue measure of an interval and how many elements in those finite sets, for instance, happen to be in that interval. So this is something that has been used many times, and it's quite convenient in its way. And what I want to discuss is problems where this is not actually such a satisfactory way of quantifying equidistribution. So issues with this Erdős-Turan inequality. Okay, so for certain purposes, it's perfectly fine, but there are others where it might not be what one wants. So I'm going to highlight 2 of them. So one is higher dimensional versions. Which feel less intrinsic, at least to me. So I'm not going to state any of these higher dimensional versions. There are many classical ones. So the thing is, usually what happens is you replace the intervals by a certain choice of types of subsets. And if you look at a higher dimensional version, meaning in R mod Z to some power, it's not necessarily clear why, for instance, rectangles should be better than other subsets, depending on what you want to use this for. And in our case, in this work I had with Theo Untrau, the issue started there because we had equidistribution not in R mod Z to the power D of certain limit measures, but we had the measure on a subtorus, and there was no canonical coordinates on that subgroup, and so it was not necessarily very natural to choose any choice of coordinates to define the rectangles that you would use for a classical higher dimensional Erdős-Turan inequality. So that's one potential issue. And the other one, which is somehow related, is what I will call lack of invariance under various transformations. And what I mean here is that suppose we're in the situation of the Erdős-Katz theorem, and you have some kind of other function g from R mod Z to R mod Z, which is continuous. Then if mu n converges to the Lebesgue measure mu, then it's a completely formal fact, just looking at the definition, that if you push forward mu n by the function g, it converges to the push forward of the measure by the function g. So that's completely formal at the level of equidistribution. But the problem is, you also might want to have such a phenomenon or principle of transformation that also applies for quantitative statements. And if you measure the convergence of mu n to mu using the discrepancy in the Erdős-Turan inequality, and you apply some continuous function, well, there will be first the problem that the limit measure G lower star of mu is not equal to mu in general. And the Erdős-Turan inequality is specifically written for the Lebesgue measure. And even if you took a function G so that this is again the Lebesgue measure, it's not straightforward just looking at the statement of the Erdős-Turan inequality, what's going to happen for the discrepancy of the image under the function G of the mu n's. Okay, so this is what we were looking in our application with Theo. What we're looking for was a more abstract or maybe a more invariant way of measuring quantitative equidistribution. And it turns out there's a way of doing this, which is in some sense was staring us very obviously. So in the face, because it's an extremely well-known way of measuring the distance between probability measure. It's this Wasserstein matrix. Okay, so they are also known as Kantorowicz matrix or Kantorowicz-Rubinstein. There's various names, but the one that seems to stick the most is Wasserstein matrix. So it's a very important concept in analysis, especially in optimal transport. But it's also very often used in modern probability, statistics, actually many fields. And as I said, it's a way of giving a distance on the space of probability measures on suitable spaces. So I'm going to give the definition. As I said, this, if you've ever seen a colloquium in analysis in the last 10 to 15 years, there's a good chance that optimal transport was mentioned. And therefore, there's a good chance you actually saw this definition because it's really become one of the most exploited tools in many parts of analysis. So I'm going to, again, work in less generality than these metrics are defined. So one small difference with the setting I was before is now we need to have a metric space. For applications, this is usually not an issue, but it will depend on this distance D. The metric space has to be complete, but it need not be locally compact. There's many cases where infinite dimensional spaces are used in this setting. So we're going to define distances between probability measures. I'll call them just mu1 and mu2, probability measures on X. This will depend on the parameter P. So it's a real number. Okay, so at some point later, P will become a prime number as it should, but for the moment, this is a terminology that's also so standard that using anything else would be a bit problematic. So we have a parameter, which is this real number, and one defines the Wasserstein P metric between mu1 and mu2 in the following way. So it's an infimum over measures on the product in a set that's called capital pi of mu1, mu2 usually, which is defined as the set of probability measures, so I call them pi, on the product of X with itself, such that if you project with on the first coordinate, you obtain mu1, and if you project on the second coordinate, you obtain mu2. Okay? So for instance, the product measure of mu1 with mu2 will have this property, so this set is always non-empty. And once you have this, then you integrate over the product the distance between 2 points to the power p with respect to this measure pi, and you take the power 1 over p. And then you take the infimum over this, and in this generality, this infimum is actually achieved. I'm not going to use that fact, but it's something that's worth knowing. Okay. So it's a definition that one finds now in books dealing with optimal transport, for instance, and so on. And it turns out to have many, many good properties. So the basic one I want to mention so altogether, there'll be a list of, I think, 4 properties, and they really show that this gives a good quantification of the notion of equidistribution or of convergence of measures. So the first one is that it does metrize convergence in low or equidistribution, at least if X is compact. So in the more general case, you would need to have some finiteness condition on the measure, but in that case, to say that mu n converges to mu in the sense of equidistribution is equivalent to saying that the distance between mu n and mu goes to 0 as n goes to infinity. So any quantitative bound that goes to 0 for the Wasserstein distance would give some kind of quantification of equidistribution. And this holds for every fixed p. So this does not depend on the choice of p. That's the first property. The second one is it has these strong invariance properties, which is what I was saying the Erdős-Katz inequality does not really have. So it doesn't quite work with an arbitrary function that's continuous between a space and another, but it works for Lipschitz functions. So suppose you have a Lipschitz function from X to not necessarily the same space, let's call it Y. And let's say it's Lipschitz with constant C. So it does not distort the metric by more than a factor C. Okay, so Y is another metric space. Then it is completely formal that, again, for any P, computing the distance after taking the push forward by the function G cannot increase the Wasserstein distance by more than the factor C. Okay. So that means any kind of quantitative statement you might have to measure equidistribution in Wasserstein metric, anytime you apply any Lipschitz function, this will translate into essentially equivalent equidistribution, quantitative equidistribution on the target space Y. So what you're losing is this Lipschitz constant. The inequality being with no implied or mysterious things means that it's also actually useful maybe when C depends on other parameters, and it will give you something uniform without having to do anything. Okay, and this invariance property is, as I said, completely straightforward from the definition. There's essentially nothing to prove, which for me is a good sign that this can be useful for the kind of things we want to do. Then the third is specific to the case p equals 1. There's a version which applies to other values of p, but is less straightforward. So when p equals 1, this is something called the Kantorovich, or Kantorovich actually, I think, Rubinstein duality. And it's a very nice functional interpretation of W1. So W1, mu1, mu2, the distance between the measure mu1 and the measure mu2 if you use p equals 1, it's the same. So as a supremum, so it's a kind of a duality between min and max. But now you take the supremum over continuous functions, which are 1 Lipschitz. And then you compare the integral of f from mu1 and mu2. Take the modulus and take the supremum over all 1 Lipschitz function. So it's a kind of a functional interpretation of the W1 metric, which is obviously extremely useful and extremely nice and pretty. So when p is larger, there's a similar statement, but the set of test functions becomes much more intricate. One might say that this suggests to actually define W1 by the right-hand side instead of this play with measures projecting to mu1 and mu2. And it's true that for what I'm going to say today, you could do it this way. You could take the right-hand side as the definition and forget about all other Wasserstein metrics. But in the general theory, it seems really that actually P equals 1, like an L1 space is pathological in some respects. And it's actually better to use other values of P, like P equals 2 in particular. Okay. And the last one, the last statement is again even more restricted. So I'm going to take P equals 1. And the space X will be very special. This will be a compact connected Lie group. Okay, and example is this R mod Z to the power D that I discussed before, but you should also think of unitary matrices or special unitary matrices or special or unitary symplectic matrices of some size. And in that case, when you take D to be a suitable invariant metric, so in the case of the torus, it's the usual one. In the case of SUD or USP2G, these are more abstract metrics defined in the theory of compact Lie group. So I should say pi invariant metric. Then there is a theorem due to Borda in the general case, and Bobkov and Ledoux for tori. So for the first case. And this inequality will look like an Erdős-Turon inequality, but for W1 on such a space, but very much similar to the Erdős-Turon inequality in some sense. So it says that for mu1 and mu2, arbitrary measures, probability measures on this group. So I'll call it capital G, because a group should not be called capital X, I think. So let me get my statement to be sure I get the right one. So we estimate W1 of mu1 and mu2. It's going to be bounded by a constant depending on the group by something like, again, 1 over T, where T is a parameter that can be optimized. And then instead of a sum of Weil sums, it's now going to be an L2 kind of average. So it's a sum over parameters lambda with norm up to T. I'm going to say what these are in a second. Then there's the dimension of the associated representation divided by another quantity that I'll define, which is kappa lambda. And then the Fourier coefficient for associated to lambda for mu1 minus the one for mu2 squared. This is a Hilbert-Schmidt norm, and everything is raised to the power 1/2 because this is some kind of an L2 right-hand side. Okay, so I should say what all these various things are. So the lambdas are the highest weights parametrizing irreducible representations of G. So in the case of R mod Z to the D, which is already very interesting, then lambda is just an integer in Z to the power D. So in general, these are elements in the cone, contained again in a lattice of some dimension related to the Lie group. Then we have, so the irreducible representation associated to lambda is denoted by rho lambda, and then it's the dimension of the underlying space. So in the case of lambda in Z to the D, then rho lambda is a one-dimensional representation, and it's defined by rho lambda of X equals exponential 2i pi the classical inner product of lambda with x. And the dimension is just 1. Then the kappa lambda is so-called Casimir eigenvalue or Laplace eigenvalue. It's essentially a variant of the Laplace, an eigenvalue of a variant of the Laplace operator. So in the case of R mod z to the d, the norm of lambda is just the Euclidean norm, maybe up to a constant multiplicative factor. And the final thing is this Fourier coefficient. I will define them here. So the mu tilde for an arbitrary probability measure mu on G and for an arbitrary lambda, what you do is you integrate over the group with respect to the probability R measure. With respect to the measure mu, the image of rho lambda of an element, you take the adjoint and you integrate, as I said, with respect to mu. Okay? So this is a linear map on the space of rho lambda. So it's a linear transformation, which is why here we have a Hilbert-Schmidt norm to compute the size of these things. And in the case of the torus, well, this is just the usual Fourier coefficient. It's a one-dimensional thing. It's just the integral over R mod z to the d of exponential 2i pi inner product of lambda with x with respect to x. Okay. So that's the this inequality of Borda. And I should say that recently there's been a preprint by Borda and Quenin, which states a version of this for other values than p equals 1. So we haven't yet incorporated that into our applications, but this should be straightforward. And this should be very useful to obtain applications where you use WP where p is not equal to 1 necessarily. But for us, we started with p equals 1, and this inequality, as I said, is highly comparable with the Erdős-Turon inequality, of course. In the case of the torus, the quantities which appear are exactly the same as in generalization of the Erdős-Turon inequality. So the bounds you obtain are kind of very similar to what one would get in any application of the Erdős-Turon inequality. But what you bound is not the discrepancy. What you bound is this Wasserstein metric. And then you can exploit the invariance properties of the Wasserstein metric to go towards applications. So let me now, in the remaining time, discuss some application. So I'm going to present the one that we have in our paper with Theo, but there are others that have already actually been done by a few people since our paper was on arXiv. And I'll mention Cornelissen, so CF also, because this kind of show how this really can give a very flexible framework for equidistribution. Oken Ringeling. And there's another by Peter Humphreys, which does the kind of Duke theorem or equidistribution on the hyperbolic, on quotients on the hyperbolic plane in terms of Wasserstein matrix. Okay, so the application we have is a version of Deligne's equidistribution theorem, which is effective and quantitative. And here again, I should say, this is not the first time that people quantify Deligne's theorem. It's very natural to try to do this because Deligne's equidistribution theorem is proved by very strong bounds coming from the Riemann hypothesis of finite fields for the underlying Weil sums. And therefore, it, in some sense, was already from the beginning a quantitative equidistribution statement. So here I want to refer to an old paper of Fouvry and Michel. which is very much in the spirit of what I'm going to describe. So from 2002, which kind of did by hand some of the things I'm going to describe, and more recent work by Fu, Lau, and Chi, probably 2023 or 2024, who have a fairly general version in terms of some version of discrepancy for Deligne's equidistribution theorem. So Deligne's equidistribution theorem is a very, very general statement about existence of limiting distribution for families of exponential sums over finite fields. And since I don't want to assume the kind of background material that's involved in a general statement, I'm going to do a special case, which is already quite interesting and important for applications. So this is going to be about hyperclusterman sums. So we fix an integer r. Now we're going to, from now on, P will be a prime again, and the Wasserstein matrix will all be in W1. Then for a prime number P and an invertible element modulo P, one can define, following Klosterman and Deligne, the so-called hyperclusterman sum, KLR of A and P, which is some normalizing factor 1 over P to the power R minus 1 over 2. And then you sum over R elements in FP, restricted by the condition that the product is equal to A, and you sum the additive character exponential 2i pi over P applied to the sum of these elements. Okay. So when R is equal to 2, then you have 1 over square root of P, and then you have X and Y where the product is equal to A. And if you express, let's say that X2 is A over X1, then you recognize this is a classical Klosterman sum. In general, this is a generalization of Klosterman sum, which occurs naturally in many problems of analytic number theory. And the distribution properties of this was established so by Deligne and Katz. So let me state it in 2 steps. So Deligne proved around 1974 that for every A and for every P, you can find a matrix that I'll call theta of A and P, a unitary matrix of size R minus 1, of size R of C, actually with determinant 1, but let's say just a unitary matrix of size R, such that the trace of this matrix is the hyperclusterman sum. Okay, so this is already an extremely strong fact because it immediately implies, for instance, because the trace of a unitary matrix is bounded by the size, that the hyperclusterman sums are bounded by R. So if you take R equal 2, you get the Weil bound for the classical Klosterman sum. So this is a special case of the Riemann hypothesis over finite fields, already quite strong. So RH over finite fields. Okay, and it follows from the work of Deligne and then from the work of Katz. So Deligne more or less proved there has to be some kind of equidistribution property for these matrices. And Katz actually determined precisely what the equidistribution properties are. And they can be phrased as follows. So if you take, okay, so there exists a Lie group, compact Lie group G sub R, such that the if you take for a given prime P all the various matrices associated to this prime, and they depend on R, I should say, because the rank is important. So there exists a Lie group which also depends on the R, such that these become equidistributed in fact, not in the group itself, because I didn't say it, but this is the space of conjugacy classes. Because these matrices are only really well defined up to conjugation, but these matrices become equidistributed in the space of conjugacy classes with limit, so the measure mu in the equidistribution equal to the image of the probability R measure. So they are uniformly distributed. That's the way to think about this. And moreover, so in some sense, this statement was already known to Deligne, except for some subtleties. But what Katz did, which is the crucial to actually understand what the statement means, is to compute the group. And he showed that the group is the space of unitary matrices with determinant 1 when R is odd. And it's the space of unitary symplectic matrices of size R when R is even. So this is what the Katz called or calls the monodromy group for this family of exponential sums. Okay, and so the first application or one example of the general form of Deligne's equidistribution theorem that we proved with Theo for Wasserstein distances is the following. So that the W1 metric between, I should give a name for this probability R measure. Let me call it mu sub R small r. So the distance to the limiting measure associated to the hyperclusterman sums with the integer r, and the sampled, so I'll write it explicitly, the average of Dirac masses associated to these conjugacy classes, viewed as element, everything taking place in the space of conjugacy classes. This is big O of P to the minus 1 over the dimension of this monodromy group. And this is the statement that we prove in full generality for any family of exponential sums where the monodromy group is also connected. It's always going to be a compactly group. It's not always connected. We're working on generalizing the statement to non-connected groups, which definitely should be possible. Okay. So in the few minutes before I end, I want to emphasize two things about this result. So one is a concrete application. So what does this tell us about hyperclusterman sums that we might not have known before? So one typical application of quantitative equidistribution is what people call often shrinking target problems. Which means you're trying to compute how many, let's say, of these conjugacy classes are in a certain set, where the set is not fixed, independent of the prime in this case, but actually becomes smaller and smaller when the prime grows. And here, so what this gives us is the following theorem. So I'm going to state it when R is odd, because the statement takes slightly different form depending on the parity. I'm going to take then a matrix G0 in SUR of C. So that's the group GR for R odd with at least 3 different eigenvalues. Okay, so in particular, it cannot be the identity. And then we are able, using the Wasserstein metric, to get a lower bound for the number of hyperclusterman sums, which are close to the trace of G0, which are close by a constant, so let's say 1 divided by p to some exponent, which turns out to be 3 times r squared minus 1. Exponent is not so important. Okay, so you see, if we just were saying that we want this to be less than some fixed epsilon, we would just want the Klosterman sum to be close to the trace of some element in SUR of C, and equidistribution will tell us that this happens at least once and with the right proportion when p goes to infinity. Now we have a distance between the hyperclusterman sum and the target, which is shrinking when p goes to infinity. And we show that this is bounded from below by, for p large enough, by a constant times p to the power 1 minus 2 over 3 times r squared minus 1. Okay, so we show existence, but we also show that there are, in fact, many of them. And what is relevant here is that this is the right proportion. In the sense that this is the R measure of the set of matrices where the trace of G minus the trace of G0 is bounded by this, approximately up to constants. Okay, so that's something that it's a statement which does not mention Wasserstein metric or anything. And the way it's proved is, well, we start with the Wasserstein bound that I stated before. This is only provable in a kind of easy way because of the Riemann hypothesis and Bordas inequality. But then the trace map from the conjugacy classes to C is a Lifshitz map. And therefore, we obtained a comparable quantitative bound for the distance between the image of these measures by the trace map. And then we have to do some construction of test function to deduce this type of things. And I'll take one more minute with one last remark, which I find interesting. I'll say it relatively imprecisely, but one can show that assuming a bound like W1 between the R measure and this average, let's say, suppose you assume that you know a bound p to the minus alpha. So I just showed that it can be proved, but suppose we didn't know the Riemann hypothesis, then we could not prove it. But suppose then that you say, okay, someone gives you a bound like this for some alpha strictly positive. Then from this, you deduce zero free strip, not the Riemann hypothesis, but a zero free strip for certain L functions over the finite field. Associated to the hyperclusterman sums. Okay, so I'll stop here, but for me, this is an interesting point because it shows that somehow bounds in Wasserstein metric, they do contain some of the most relevant arithmetic information that go even into the proof of equidistribution. In this case, it's not the Riemann hypothesis, but the zero free strip is already something very, very strong. And I find that intriguing. Yeah, so I'll stop here.